We're getting ready for our first homework set that introduces 2D NMR. And I wanted us really to get a mastery of other techniques before we started to introduce 2D NMR into our toolbox. And so today what I'd like to do is to do sort of an introduction to 2D NMR spectroscopy and talk about the principles and some of the basic experiments. So in one-dimensional NMR, it's called one-dimensional because we have a single frequency dimension. So we pulse and then we observe. And as we observe, we get a free induction decay. We get a signal where we're talking electrical amplitude, voltage versus time. And when we Fourier transform, we convert the time dimension. Basically, this is seconds, so we're getting amplitude versus time. We convert the time dimension to a frequency dimension. So we would, here's our 1 ppm, 2, 3, etc. And this is frequency, where we're dealing with a frequency in hertz, or hertz translated into parts per million. So in two-dimensional NMR, and of course that is a two-dimensional spectrum, but in two-dimensional NMR, it's again not the dimensions of the spectrum, but rather the fact that now we're going to have two time domains. So the general idea for all of the 2D NMR sequences, they differ in the variety in terms of the exact pulse sequence. But you pulse, you wait, you pulse again, and there may be more pulses and more waits, or the wait may be split up, and then you observe. And for the wait time, you vary the wait time. So you may wait in one set of pulses, you may wait 1 millisecond. In another set of pulses, you may wait 2 milliseconds, or let's just say microseconds for a typical one. In one set of pulses, you might wait 1 microsecond and 2 microseconds. And so you'll get increments in the T1 dimension. So this is the T1 dimension, which we increment. And then we observe, and this becomes the T2 dimension. Whereas here we didn't need to specify T1 and T2. And at that point, we collect a set of FIDs. So basically, you collect FIDs for all of your different increments. And you do a 2D Fourier transform. And you get a spectrum that's typically plotted like this, where effectively, these plots are contour plots. So think of a topological map. You know what a topological map is, a topographical map. So traditionally, we plot it in a topographical map where each contour represents intensity coming out of the board here. But again, our two dimensions are that now we get a frequency dimension here, which we call the F2 domain. And here we get a frequency, which we call the F1 domain. And we've talked a little bit about digital resolution in the past. The digital resolution, in part, in this spectrum is determined by how long we collect in the time domain. And that's the same over here for the F2 domain. But the F1 domain is determined by the number, the digital resolution is determined by the number of increments. And often for a quick and dirty experiment, you'll do about 256 increments, and that'll get you kind of sufficient digital resolution. I think James knows from last year's final that when we wanted to do up spectra nice and get you as much resolution as possible, we'll often go to 512 or sometimes even go a little nuts with 1024 increments in the F1 domain. You're going to start to collect spectra, and you'll be reading about, if you haven't already, you'll be reading in the UC Nmr manual about various parameters that you're choosing. And it's good to keep in mind that this is going to determine your sharpness in this dimension. All right, so I want to talk about the types of experiments now, and then we're going to eventually get to a specific example from this week's homework set. All right, so there are two basic types of experiments. There are correlation experiments, and these give rise to information on proximity. I'm sorry, connectivity. My mouth is moving ahead of my writing. And then there are Overhauser effect experiments. And there are also one-dimensional Overhauser effect experiments. We'll talk about them in a lecture or so. I think it's next lecture. And these give rise to information on proximity. So let me put these into very clear context. So you already understand the concept of connectivity. And I think everyone on the exam, maybe save for one person, did problem number 1 of part 2. So this molecule should be very, very familiar. Tetrahydroisoquinoline as an example. And we saw that there were 3 sets of resonances in the aliphatic region. And we saw a triplet, a quintet, and another triplet. And most people were able to infer the connectivity of this molecule. Most people were able to infer that the triplet was coupled to the quintet, and this other triplet was coupled to the quintet because these were the only aliphatic couplings. So most people were able to look at this spectrum and recognize, oh, we have a CH2, CH2, CH2 chain. Well, a cozy experiment is going to give the same type of information, but without having to use this type of inference. So it's another way of building up this type of experiment of connectivity. People have also in the depth experiment been able to say, oh, that's a carbon in the aromatic region with a hydrogen attached, because it's a CH group. So they were able to infer that these carbons had hydrogens attached, and that's going to be our Hmqc experiment. Now, we haven't done anything with proximity, but I'll give you a very relevant example. Let's say we have a cyclopropane ring and we have a methyl group and an ethyl group on it. And let's say we also have a carboxy ethyl grouper on it and a hydrogen on it. And we want to tell the stereochemistry. We want to tell if the hydrogen is proximal to the methyl group or if it's proximal to the ethyl group. In other words, we want to know about proximity. And this is where the Overhauser effects experiments come into being useful. Now, we're only going to learn a number of 2D experiments, I think, that you can count, if not on one hand, let's say on two hands, because I don't want us to get caught up in the alphabet soup of experiments. We'll really talk about 6 experiments primarily, and then a couple of others. So let's talk about what I'll call core 2D experiments. So COSY is certainly the most fundamental of 2D experiments. It's not the first one ever developed, but it's the one that's sort of most useful as a workhorse and very easy to run. It stands literally for correlation spectroscopy. Another one very useful is Hmqc, which there's an older variant of the experiment called HETCORE. They differ in whether you're observing in the proton dimension or in the C13 dimension. Both of them are heteronuclear correlation. Typically linking carbons to hydrogens, and we'll see examples of that later on in today's lecture. An experiment that's kind of like the COSY is called Toxi. It stands for total correlation spectroscopy. It's very good for picking out spin systems because all of the resonances in one spin system within limits give cross peaks with each other. Another experiment that's very useful is called Hmbc, or heteronuclear multiple bond correlation. We'll call it a long range HETCORE. Again, HETCORE is the older version of the experiment that's carbon detected and one that's more difficult to do. Very useful for putting the pieces together. So maybe if I were annotating these, I'd say basic connectivity, CH connectivity, spin systems. I'll say putting the pieces together, and I'll talk more about this in a few lectures. I think you've already seen examples For those of you who did the second problem in the exam, and very few people got the right answer on the second problem in the exam, which was a hard problem and in a way ambiguous, I'll give you a perfect example. Many people were able to figure out that we had a 1,2,4 tri-substituted aromatic group. Many people were able to figure out that we had a CH2-CH2 chain, that we had a ketone as a carbonyl, and that we had a methyl group and a methoxy group and an OH group. And then a lot of people struggled with how these various pieces got connected together. And the Hmbc experiment is very good for that type of thing. Then two other experiments, Nosy and Rosy. These are two flavors of Overhauser effect experiments. And I already gave you an example of stereochemistry where it would be useful. And of course, you've seen this where we've talked about, say, stereochemistry of a cyclohexane ring where we were using coupling. All right, so what I'd like to do at this point is sort of diagram these experiments out, or at least 4 of these experiments, the first 4 of what I've called the core experiments. And I'll diagram them all out with propanol, with 1 propanol. And what I'm going to show you, I made little schematic diagrams for the handout. But what I'm going to show you then for COSY is we're basically going to, and I think I'll be kind of neat here and draw my arrows to my hydrogens. We're going to see that we have this type of correlation and this type of correlation, just like I hinted at with the tetrahydroquinoline example. For Toxi, we're again going to get these 2 correlations, but we're going to add in 1 more correlation. Those correlations will appear as cross peaks. For Hmqc, I'm going to diagram this out as follows. And say for Hmqc, what we're going to see is how the hydrogens correlate with the attached carbons. And for Hmbc, I'll give the same diagram, but say now what we're going to be doing is we're going to be picking up J2CH. So this is effectively picking up J1CH. It's picking up 1 bond coupling. for Hmbc, we're going to typically be picking up J2CH and J3CH couplings. And of course, in the case of allylic and other long-range couplings, we might even pick up the occasional J4CH for longer range couplings. But the way I'm going to diagram this out is as follows, where the hydrogen on the methyl group is correlating with the carbons that are 2 and 3 bonds away. The hydrogen on the methylene group is correlating, in this case, we only have 2 and 3 bond couplings. And the hydrogen on the methylene group next to the oxygen is correlating with 3 bond couplings and with 2 bond couplings, like so. Now, if you notice, for all the techniques I've drawn out, this one is the one with the most arrows on it, the one that may be the most confusing. And the first thought, and the reason we're not going to introduce this into the first problem set, is this can be like drinking from a fire hose, Hmbc. But when you have a targeted problem, like where is that carbonyl group attached, or where is that isolated methyl group attached? The problem I was talking about that we encountered in part 2, problem 2 on the exam, where people were trying to struggle to put together the CH2 group and the methoxy group and the methyl group and the 1,2,4 trisubstituted aromatic and the carbonyl group and the hydroxy group. This technique can be very valuable when you know what questions you're asking. So I'd like to show some schematics at this point and go to the handout so that we can at least get familiar with the various techniques. All right, can people see my screen here?
Yes.
Great. All right, so this is my little diagram for propanol. And this is a representation of a Hmqc spectrum of propanol. And the first thing I'd like to show you is the actual Hmqc spectrum is the square in the center. The spectra along the side are spectra that were taken separately and superimposed, so they're one-dimensional spectra. And so what we have over here is this dimension here is our F1 dimension. Or the F1 axis. And this dimension here is our F2 dimension, or F2 axis. And then you'll see that we have, I've put the 1D spectra over here. And I'll just give you a little bit of a calibration here. If we call our peaks A, and we're going to all be doing this in the future so we can all stay on a common language, if we number our peaks from downfield, letter our peaks from downfield to upfield in the proton dimension, A, B, C, and D, most of you would be able to say, okay, that most downfield triplet is HA, that singlet is HB, it's not coupling, the OH group is exchanging rapidly. the sextet is C, and the triplet upfield is D. And we have the same thing over here, A, B, C, D. So every peak gives a peak with itself. In other words, this is the peak on, we call this the diagonal. So this is the diagonal. And D is with D, and C is with C, and B is with B, and A is with A. But what we're seeing here now are what we call cross peaks. And they're symmetrically disposed about the diagonal. So we see A cross C over here, and that, of course, corresponds to this correlation. And then we see the same thing over here, not new. It's just, you know, basically we could call it C crossing A. And here we see C with D. And here we see basically D with C. And so usually I just pay attention to one side of the diagonal or check or cross to make sure that we've got it right. So we're getting all of our HH couplings, including long range. So this is both, this would be J2, HH, J3, HH, long range. And in general, as well, long range couplings. In general, the taller, the stronger the coupling, and the taller the peaks, the stronger the cross peak. So if you have a very weak cross peak, you're probably going, if you have a very weak correlation, a very small J value, you'll probably have a small cross peak. If you have a stronger correlation, a bigger J value, you'll have a big cross peak. If you have a very short multiplet, you'll probably have, if you have two very short multiplets, you may have a weaker cross peak. If you have very tall doublets, you may have a stronger cross peak. Any questions about the COSY?
Quick question. Can you clarify what you mean by like small like large, like cross peaks? Like does that mean it's just like more concentrated with the shapes?
Yeah, so remember I talked about contours. So remember I said that we will typically plot contours. So a strong cross peak will have many contours. A weak one might have fewer. And you yourself choose the level when you plot this. James will try on the exam problems, and we've tried in all the homework problems, to choose the levels so you see as many cross peaks as possible. If you go too high, you'll miss some, but if you go too low, you'll get down into noise. But nevertheless, very weak couplings like meta-coupling on a benzene ring might be harder to pick up. Or if you've got like a Lillich coupling, you might or might not pick it up depending on where you've cut your levels. Other questions?
James, I just pulled up the COSY I took for strychnine last night in Topspin, and Topspin allows you to visualize both a contour plot as well as sort of a topographical image. Would you mind if I shared my screen? I think it might be useful for the...
Let's do that at discussion, because I don't want to run too late today. Sorry.
Sure thing, no problem.
Sorry, I want to get to one real example. So I think I want to move along at this point. That's weird. I have two COSYs in there. Huh. All right. Anyway, here's an Hmqc. So the same molecule. So now in the Hmqc, we have our C13 axis is our F1, and our H1 is our F2. Again, we have our peaks A, B, C, and D. We have our carbon lines, our carbon peaks 1, 2, 3, and 4. And remember, this is a separate carbon NMR spectrum that's superimposed. This is the actual 2D spectrum. We have no diagonal. And every carbon gives a cross peak with the hydrogen. So carbon 1 gives a cross peak with hydrogen A, or with proton resonance A. And so we can say, oh, that's C1. And carbon 2 gives a cross peak with resonance C. So we can say, oh, that's C2. And carbon 3 gives a cross peak with hydrogen D. And so we can say that's 3D. And so that's our basic Hmqc spectrum. And we will typically start with the Hmqc spectrum. And again, I'm going to head along to an example in just a second. All right, here's the Toxi spectrum. The Toxi spectrum is just like the Cozy spectrum, but we get all spins in the spin system. And there are limits on that depending how far you go, but we can start by saying all spins in the spin system. In other words, we still have our diagonal. We still have our peaks corresponding to A, B, C, and D, A, B, C, and D. And again, this is our propanol example. And we still have our A cross C peak, and we still have our C cross D peak, but now we get a new peak that's A cross D. And that's telling us that these two are part of the same spin system. And this is particularly useful when you run into crowding. So when you have a very crowded spectrum and you just can't work your way through because you've got some mild overlap, then it can be very useful. Useful for overlapping resonances. All right, any questions about the Toxi? All right, last one I want to show you is the Hmbc spectrum. And so again, I'll give her a little schematic of the molecule of 1-propanol. And again, I'll number, I do so rather slavishly, number all of our carbons, letter all of our proton resonances. And now we get a lot of cross peaks. And you'll notice, we'll just look here for a moment, you'll notice that 2 is crossing with D, and 1 is crossing with D. And so you're saying, okay, here we're picking up our, this is our J2CH. And here for our 1 with D, we're picking up our J3CH coupling. And as I said, at this point, it seems rather esoteric, but when you've got to place an isolated methyl group, or you've got to place that CH2 group on the ring, it can be very useful for putting the pieces together. And so I'll just annotate this on the bottom. Any questions about HMBC?
Quick question, Dr. Nowick. I was wondering if you have any tips on distinguishing between the 2J, J2CH and J3CH?
Nope. And that is the frustration of it. Often, well, there's no easy way to tell them apart. It's picking it up only on the J value, but often you'll be able to use logic to do this. For example, let us suppose you're trying to place a methyl group that's isolated onto a carbonyl. So let us suppose, for example, that we have the situation that we have had in problem number 2. And we have a methyl group that's isolated, that's a singlet, and we see that that methyl group, and here we have, let's say, a triplet. And we see that that methyl group gives a cross peak with the carbonyl carbon, and it gives a cross peak with the carbon that's associated with the triplet. But you know that that methyl group isn't J coupled to that carbon that has the triplet on it, because that they would otherwise split each other, and it's a singlet. So then you'd say, aha, that isolated methyl group must be on the carbonyl. And you'd be able to place it that way. So it's usually a logic exercise. Other questions? Good question. All right, I want to move on to one real example. And again, I'd like to make a pitch for the grids. I know some people have picked these up from James. Even if you are working on a computer screen or an iPad, they are super useful for measuring integrals. They're super useful for looking at where cross peaks line up. You can slap it right on top of your computer screen or your iPad. Or if you're clever with Illustrator, which I think now everyone has access to, you could actually physically impose this grid on top of your PDF using layers. So I believe everyone now at UCI has access to Adobe Illustrator. It might even be doable in PowerPoint. I do not know. Anyway, I love it. Here's an example from the homework. It's a fun little problem, not too hard. And we look at the spectrum, and I so urge people. So the question is, what's the structure of this molecule? And I so urge people to start with the mass spec and start with the IR spectrum. And we look at the IR spectrum here, and we see a carbonyl, and that carbonyl is at 1743. And one of the things on part 1, problem 1, I really wanted people to be able to do was read their spectra, whether they were digitally marked or just in analog, and be able to look and say, okay, that's a carbonyl, and it's high for a ketone, and it doesn't look like an aldehyde. It's probably an ester. And sometimes, but not always, we can see the CO single bond stretch depending on how crowded the fingerprint region is. I generally don't rely on this because it's pretty hard to be certain, but it can be useful. And I look at the carbon NMR spectrum and I see 1, 2, 3, 4, 5, 6, 7 resonances. And I worked out my integrals with my grid and I saw that I have 1 hydrogen, 1 hydrogen, 3 hydrogens, 1 hydrogen, 1 hydrogen, 1 hydrogen. And then if we look here, you'll see we have a doublet and we have a triplet that's making up this, which totals to 6 hydrogens. So we've got a couple of methyl groups here. I notice that I have, and you should also pay attention to your chemical shifts. I look at this. Maybe this is a CH3 next to a carbonyl. It looks like from this pattern here, I have a CH3 next to a CH corresponding to that doublet. And it looks like I have a CH3 next to a CH2 corresponding to the triplet. I go ahead and I think about my molecular formula because we're a 130 molecular weight. And just from my 7 carbons that I've seen and my tally of hydrogens ended up being 14 hydrogens. And if I have an ester, that accounts for 2 oxygens. So that works out to 130. And I have 1 degree of unsaturation. So if I have a carbonyl in there, I have no double bonds. Oh yeah, another thing I wanted to caution people on. Pay attention to your carbon chemical shifts. Look at that carbonyl. It's 171 ppm. That's probably an ester. That's probably not a ketone. A ketone's going to be down at, if it's aliphatic, it's going to be down at 205 to 220. So that is probably an ester. Try to read as much as you can from your spectra and always be uncertain a little bit. Maybe it could be a conjugated ketone, but even a conjugated ketone wouldn't bring us down there. All right, so we've got a bunch of stuff going on here. And to be honest, you could probably figure out your molecule just from what you have. You know that you have 3 CH3s in the molecule. You know that you have a couple of CH2s in the molecule. You know that you have a CH in the molecule. And you know that you have a carbonyl or at least a quat in the molecule. So you could probably piece this together just from the information you have here. But I want to show you how to do it analytically. And so the next thing I'm going to do is I'm going to turn to the Hmqc spectrum. And as I said, I am very slavish about lettering and numbering my resonances. So we haven't put the carbonyl on the edge here, or Silverstein hasn't. So we start at 2, 3, 4, 5, 6, 7 on our F1 dimension, on our carbon dimension. And again, I will slavishly label my peaks A, B, C, D, E, F, G, and H. And then I'll look at my cross peaks. And we've got 2 with A and 2 with B here. And so I will go ahead and transcribe those numbers up here. And this is going to be my Rosetta Stone for solving the problem, where I have the numbers linked with the letters. And then as we continue to see, we've got 5C over here. So I'll put 5C over here. And we've got 3D over here. So I'll put 3 over my D. And we've got 4, E, and F. And so clearly with the 2 protons that are non-equivalent on 2, we see that we have diastereotopic protons. And with our 2 protons that are on 4, we see we have diastereotopic protons here going on. And if we look at this, this is a good example because this relates to something else we saw in the exam. This is part of, so A and B are part of an ABX pattern. And so you notice in an ABX pattern, very often you will see the resonances tenting into each other. You'll see that the inner lines are bigger, taller than the outer lines. I guess I can't write that small, but I'll say taller and taller. In other words, it's not just a doublet of doublets. Each of these is a doublet of doublets that are tenting into each other. In other words, it's not 4 even lines and 4 even lines. It's 4 lines with the inner ones bigger and the outer ones smaller. And that is so characteristic of an ABX pattern. All right, so we've got our ABX pattern there, but back to this, we've got our diastereotopic protons. Here's a case where my grid really would shine. It's nice also to be able to zoom in and zoom out, but if you can't or don't have that ability and we give you an expansion here, you may also be able to see it. Here's a little expansion of this region just blown up larger. And we have our G and H resonances. And so you can clearly see we have 6G and 7H. You could also make that out here. And so we can finish our labels, finish off our Rosetta Stone with 6G and 7H. All right, at this point, now we're ready to build up our molecule and use the COSY for this, and I'll show you how we do that. So at this point, again, very slavishly, I'm going to transcribe things. We will normally plot both spectra along the axes. Here, for the sake of convenience, they've only plotted one, but we will typically plot on both axes the proton spectrum. Remember, this spectrum doesn't come from the 2D spectrum, although you could plot it from the 2D spectrum, but it's kind of ugly. We do a separate 1D spectrum and superimpose it. So I'm going to transcribe our numbers 2A, 2B, 5C, 3D, 4E, 4F, 6G, and 7H. And now we're just going to start and identify our cross peaks. I'll go ahead, I'll draw my diagonal. Let's see, I meant to put a ruler out handy. I'll put a little ruler down on my iPad. So I've drawn my diagonal. And now we can see, okay, we've got 2A cross 2B. That's not especially useful. So there's our, I'll just start. That's not really useful for much of anything. C2, HA, HB. And pay attention to your chemical shift. Those two resonances are at about 3.9 ppm. Those two resonances, that's certainly going to be a carbon connected to an oxygen atom. All right, now things start to get interesting with the next two cross peaks because now we've got 2A with 3D. and we've got 2B with 3D. So now that takes us to C3HD, a methine, because we knew it was a methine from the depth spectra. And now let's continue with our cross peaks. 3D over here crosses with 4E, and 3D crosses with 4F. And so we can continue to build C4, HE, HF. And if we look hard here, and again, it helps to have a grid, but if not, you probably can make out from the shape of the cross peaks that this cross peak is corresponding to the 6G. So this is 3D with 6G. I'm going to repeat this with a finer nib. And so we can continue to build up our molecule. C6H3G is attached to HD. And let's continue now. We go over to this cross peak here, and we get 4E with 4F. That's not particularly useful because that's our diastereotopic protons. And finally, we come over here, and now we've got 4E with 7H. And again, my grid could be very helpful here. And we've got 4F with 7H. And so we look over there, and that builds out our chain. And if we're keeping tally at this point, now we haven't taken care of C5, H3E, H3C rather, and we haven't taken care of our C1 carbonyl. But in this case, it's pretty easy to put the pieces together because we've built up an entire chain. We've used logic to place the oxygen. We already have a suspicion that that C5H3C might be a methyl ketone because it appears at about 2 or 2.1 ppm. We pretty much have a suspicion we might have an ester. And so we can finish our picture of the molecule like so, drawing in the last couple of bonds. And so that completes our analysis. That completes our analysis of this molecule here. We've gone ahead, we've identified the structure. In this case, as in the other cases on today's homework, this week's homework, it's relatively easy. We probably could have done that without COSY and Hmqc, but this is a nice introduction to how we use these tools to build up structures.